Bismillahirrahmanirrahim. Assalamualaikum, everybody. So today we are going to have a lecture number 9. So where the topic is digital terrain modeling. So let's start with this lecture 9, digital terrain modeling, with some information. As usual, I want to know your mini project. So how is the progress? Hopefully that two of the group have made already perhaps almost 85% above for the report and also for the YouTube presentations. We will make a YouTube presentation. So make sure this mini project still in progress. You have a progress on it. While written test, so this one you will have during the test week, is the last following weeks of the last week lecture. So this one will be cover the whole of the chapter. And this one practical test we have done before this. So we have to do it smooth plan. So it will be good for the plan that we supposed to have in this semester. So if you look at the assessment for ECG579 before this, it will be assessed based on where they have for final examinations and also the written test, practical test, lab report, also project. This one is mini project. So it covers report and presentation. Presentation means you do it in online. So better to use YouTube so that people can access smoothly. So in here we have 40%, 15%. So according to the percentage, so the total will be 100%. But this one is from the previous. So for this semester, based on MCO, the situation. So FKA management have decided to make 60%, and also 40%, where this will be the assessment. So we don't have any more the final examination. So we only have written tests, practical tests that we have done, assignment, lab report. This one covers 30%. So make sure you submit all the lab report and also the mini project, like I mentioned to you. So the report will cover 20% and the YouTube presentation will cover 20%. The whole will be 100%, inshallah. Okay. So according to our plan, so based on this one, week 14, 24th June 2020, so we should have lecture 10 and lecture 11, whereas 1st of July 2020, so we have lecture 11 and lecture 12. So the only lecture that I still not covered is lecture 9, 10, 11, and also 12. So all of this, inshallah. So this lecture that are going to be presented will be lecture 9. So it will be continuously after this lecture 10, 11, and 12. So I will do as an online recording in YouTube, so that you can get back the point in this lecture, and maybe you can put some comments in the YouTube so that people other your colleague especially can get some information and knowledge, sharing knowledge inside of the lecture. So this is what I mentioned to you. The test week will be following after week 15. So I think you also got this information from FKA administration. Okay, so about the test, about the practical, this is under lab. If you notice, this is lecture, and this is lab. So under lab, we also have done before this lab 1 until lab 7, and then we have a practical test already. So the last lab that we still not finished yet is lab 8, 9, and 10. Okay, this one. So will be make in online recording. So I will give some briefing about this lab 9 and 10. So at the same time, so maybe we will have a revision. So there's the last that we can discuss, inshallah, during Google Meeting or maybe in WhatsApp or whatever communication online. So let's start with our lecture number 9. So the learning outcomes. So the learning outcomes for lecture 9, which is digital train modeling, it will cover digital representation of three-dimensional surface. So at the end of this subject also, the student may understood about the DTM interpretation based on slope models and hydrological models, intervisibility, and last but not least for this lecture 9, digital train modeling is DTM visualization. So we go one by one. So for your information, when we talk about DTM or digital train modeling, so it covers the digital representation, of course, of 3D surfaces. So as you can see from these small figures, just to show to you the difference between DEM and also DTM. So if you look, basically the surface are continuous phenomena rather than discrete object. Of course, in the surface of the Earth, normally there are different objects on the surface of the Earth, such as like trees, house, and the other object, etc. To fully model the surface, one will need an infinite number of points, which in turn require an infinite data storage. Yeah, correct. So to fulfill in the data storage, especially we need the data such as like the object of its coordinate x, y, and z, and maybe needs also metadata for the object. Okay, then can we present the continuous surface in a digital form using infinite amount of storage? So what that you can give, what's your idea actually? Can we present? So maybe you can answer also in the YouTube presentation for this lecture number 9 in YouTube. So I want to know also your understanding about this one. Okay, so I just let you all to put some ideas to the comment in the YouTube. Okay, DEM and also DTM. So when we talk about DEM and DTM, so DEM it represent digital elevation model. It will represent digital elevation model. So normally when we talk about digital elevation model, it is a raster of the spot height. So meaning of the spot height, it will get all the height of each of the object. If you look from here, okay, see if you can see, this is DAM. So this is the real situation. So it has a train, space of the Earth. We got tree, you also got house, and also the other trees, So the digital elevation model, if you look, it will take all the spot height. So even though houses also, so it will take the trees also and also the other tree. Compare with the digital terrain model. So when we talk about digital terrain model, it generates from any digital surface digital representation of a topographic surface, meaning that topographic surface it only take the height of the surface only. So if you look from here, it doesn't take other object except the surface of the earth only. So it's called as a digital terrain modeling, DTM. Okay, hopefully everybody understand the difference of both DTM and also DEM. Okay, the nature of DTM. So we only want to know what is the nature of DTM. Is a simplest digital representation of a portion of the Earth's surface, and also can be used as a digital model of any single surface. For example, like geological horizon. Maybe you have learned already in semester 1 or 2. The I call the subject of geology. Also, we can identify the air temperature or pressure and also the population density. So this one also can be used. So the digital terrain modeling actually encompasses general tasks including digital terrain model generation, and also the manipulation. Okay, we will look after this. The interpretation, visualization, and application. So all of this is can be a task after we have digital terrain modeling. So if you look, actually it comes from the below here, and this is the reality that you can see from the surface of the Earth. Then from here it goes to data captured. So normally data captured can be from satellite image, and also can be aerial photo, and also it can be from any sources, drone also could be. And then from all the data that have been captured, so it will be manipulated, and also just directly can be generate if the data is fully complete, full complete. But manipulate ni, it doesn't mean you want to cheat something. Manipulate ni, like I mentioned to you from the previous lecture, for example, if the buildings hidden by cloud, for example, satellite image. So whatever is supposed to be, so it should be the corner of this building, perhaps it will be seen like this one. So this is what we call as one of the factors that we mentioned as a manipulation. So this could be its coordinate. This we already know from the satellite. Two of these, 1, 2, and 3. But except the fourth coordinate ni, we because it hidden by the cloud, so we can manipulate it. So let's say if we want to confirm it, to make sure that it is a right coordinate at fourth coordinate, so maybe we also can go to the fieldwork. If the fieldwork, we can go there easily. Let's say this building is like in other countries, it's very difficult for us to go there, so perhaps we can get manipulation. So that's why we have a term of manipulation. Generation is if we don't need to have any manipulate to have because it has complete already the coordinates visualization from the satellite image and aerial photo or drone or other source. So all of this one generation manipulation, so we can create the DDM. So DDM, because why we use DDM here, because we also include the object, because if you look from the previous, it get also the spot height of the object. So yeah, we need DEM. So under DEM, we have visualization and interpretation again. Visualization, we need to visualize all of the object. For example, like tree, house, etc. Interpretation again. So let's say if the object we cannot see very clear, so perhaps the object we can make some interpretation, but based on we need to validate first. So that we want to validate, perhaps we go to the fieldwork, or maybe we look the same characteristic or classification of those object, and that might be we could not very clear to see it in the satellite image. So all of this, all of this one, so we can apply into the GIS, software GIS. Therefore, from the application of GIS, we can make some analysis and get the results. So that's the the DTM task actually. So the interpretation of DTM is most valuable as a basis for the extraction of terrain-related attributes and feature. And of course, it's very most valuable. And the information may extracted. Some of it we make some analysis to visualization, and sometimes we can make some quantitative analysis also. If we get the data, then we can calculate it into GIS software. Okay, so the objective of data interpretation is the derivation of geomorphometric parameters, of course. So when we talk about geo, something related with the coordinate, also the surface of the Earth. So the most frequent use of general geomorphometry is the derivation of slope values. So we need to understand also the slope values, the interpretation of landform features, and also the derivation of drainage network. So when we talk about slope model, actually slope is a vector, and it has a direction and length. So the important thing here is it has a direction and length. So a slope, this slope actually can be measured by its horizontal angle, slope, and also azimuth. We will look, we will see for the next slide where is the slope and also aspect in the slope. So a common algorithm to calculate slope is the one generating slope values from the normal vector. So what actually is the normal vector of the surface? So actually the normal vector is the vector which is perpendicular. So when we talk about perpendicular, so it will be like 90% to the surface with the direction pointing away from the surface. So to make it clear, you can see from here the direction and what is the slope and what is the aspect, and it's down. So you can zoom it. So this is the the angle or the slope. Start from the z coordinate, so go down or maybe go up. So with that direction. So z to x or z to y. So whereas the aspect, so the aspect is angle of x and y. So that the difference between slope and aspect, slope and aspect. So that's why the slope we have angle and also we have the aspect. Okay, good. So how did they use a normal vector into GIS? So they have formulas. So the formula, basic formula for mathematical principle. So they make such as like this one. So actually this is the proven. So if you can see from the figures, this is the angle of ZOH. ZOH, so it will be 90%, which is equal also with NOS. NOS here. So it will be 90%. Therefore, this is the formula that we can use, which is here. So which is delta prime, which is 90% minus this one. Then we can get. So actually there is the mathematical principle formula that you have learned before this. So this is the expression of a slope. So normally you also want to show you the mathematical principle where they have tangent, of course lah, tangent delta h divided by d. For example, if you want to, if you want to have cos, cos also, perhaps we also will have this kind of what we call to get the delta. For example, like this one. Okay. For example, like this one. So we try to put, for example, okay. For example, this one. This one is what we call as let's say z coordinate. Sorry, let's say z. So if you want to identify cos delta, d over z. It will be like that. So about the calculation of slope also, this is also one of the equation that they normally use in GIS, where the programmer try to put this formula into GIS, and therefore we can be calculated into GIS. So from there, you can visualize the image of the surface of the Earth itself. So this is what look like the slope map. From the left is the original. So you can see from here it's original, and the right have been derived from DM. How that it derived? Like this one, calculation of slope that had been put into GIS software. So let's see again with the aspect. So if you still remember what is aspect just now, aspect is from angle from x to y. So the direction of the normal vector in the degree close y is from nodes. So nodes, for example here, 300 ni north to northeast, east. So it depends. Normally this one is more related with x and y. So the calculation of aspect also have been put into GIS. So no need to no need to memorize of this one. Just to understand that they have a formula actually have been done by programmer that they program put this equation into GIS software actually. So you can look by using this equation in GIS, so they can develop the surface of the Earth will be like this. It looks very smooth. GIS software, not actually smooth lah, but I mentioned smooth is the equation have been make the surface of the Earth become a reality. So this is what we call as an aspect map. Whereas curvature is a slope changing rate along a given direction on a slope. So it describes the nature of mass movement on a slope. And normally it use curvature include mean curvature and contour, plane curvature, and also the profile curvature. So you will look to this what means by mean curvature, contour, plane curvature, and profile curvature. Okay, so these figures might be make a very clear picture about like what I mentioned just now. So when we talk about type of curvature, so if you look profile curvature mostly is like longitude. So it goes from this direction to this direction. Okay, so you can see. So this one, this one. So it goes here. Whereas the contour curvature, so when you look contour curvature is latitude, shows you latitude. So the connection between profile curvature and contour curvature in here. So there will be a maximum slope. Okay. So how that they calculate in the curvature, they will use this formula. So no need again, no need to memorize this formula actually. But you need to understand actually this actually maybe there has a lot of formula that can be used by programmer. I mean programmer, they put all the equation into GIS software before the GIS user can use it to make some analysis based on DTM. So this is examples that they can use to identify, for example, the mean curvature. So the mean curvature, if they want to get it, so yes, they can use this formula. Also to get the profile curvature, so this also formula can be used. Counter curvature, use this one, and all of this one will be used in GIS software that have been programmed by programmer, so they can get the equation into GIS, so the GIS user can use it easily. But not easily lah. I mean, GIS user must understand which menu tools in the GIS that they can create the DTM. So use of curvature, maybe some of it they use by using convergence and divergence. So if you look from here, divergence is at the bottom, so convergence at the top. So it shows the direction, that one. So even though the use of curvature also can be used as acceleration and deceleration. So acceleration is very fast and very steep, the slope, and so this one is not very steep. Deceleration. This is the thing that they can use curvature based on the real issue. So this will be the image will be look like for the contour curvature, like you see from the satellite image or map, also profile curvature. So there are different between contour curvature and also profile. Contour is like especially want to look the height, each of the level. Profile curvature mostly they want to look longitude, latitude, that you may like you can see from these figures. Okay, so hopefully everybody understand and very clear. If not, just can ask to the YouTube comments. So from there, maybe we can sharing our knowledge. Some of your colleagues maybe can give some answers, or later on I also can give some answer. Maybe you can go to other link to show that the answer may be given also from other YouTube link based on GIS. So next we go to hydrological models. So when we look at the hydrological models, also have been created, created based on DTM. Where DTM, digital terrain model, is contain sufficient information to determine pattern of drainage and water sheets because it has Z coordinates. So therefore, it can model So it comes as a drainage modeling. For example, locate along the steepest downhill, so it can get some target area. You can see after this the figures, it shows how that we can identify it. So the algorithm will always choose the direction of the maximum relief and search stop at the location where no more downhill neighbors can be found. So this is one example. The application, we use raster data to illustrate the algorithm. Of course, some of the data, but in this case, they use raster data. So when we talk about raster data, if you still remember, they also have some information in the data, in the raster. So the drainage network delineation, so it has such as like flow direction, so how to determine the watershed, to determine the drainage network, to get the characteristic of automatically derived network, such as like grading pitch, the number of stream joining, a junction, also junction angle. So if you look the flow direction, for example, you can see from this one, you can move with the flow direction based on our choice, how that we want to make it. Or maybe it come also from the data itself. So from there we can make some justifications. For example, like here, we assume only 8 possible direction. It will go up, right, right, down, right. So all of this is the implementation. For the analysis, number of the move direction can be clockwise from up, down. Water is assumed to flow. So therefore, we get such as like this one. So this flow direction, and we make it 1 8, for example. So the movement. So from here we can get the movement of the drainage. Watershed also is defined as an attribute of each point. So actually all of this slide, I just want to tell you how that it derived by equation and how that the water flow. So because of the factors of the surface itself, so that's why we can look the movement. So from here, maybe the level of the surface in here is very high compare with here. Compare with here. So this at last, we can get some derivation of the watershed. So the colors shows the different characteristic. So it will be good when we have DTM to show the map of the watershed itself. Okay, else like drainage network. Okay, this one also can be used to derive drainage network using flow accumulation. So from there we can estimate, and also from here we can apply it into the construction, so the contractor can cut and fill where is the good directions for drainage to flow. So from there actually it also can get from the GIS and the maps itself, and so from there the engineer can design very well. So it will be good when we use GIS based on DTM to identify the drainage network. So at last, this shows to you the drainage network. The original drainage network come from this location. So from here, actually, we can derive, we can make some flow accumulation. So here also we have effect of threshold. So what I mean by threshold? So we try to make sure that if possible, we can reduce the threshold. So when we reduce, so actually we can get better visualization compared with this one. So let's say if here threshold is 100, so there's a lot of what we call as flow. So if we reduce it, so means reduce, we put some increment of the threshold. So the water flow that we can, might be some of it can combine, and then we can justify it very well from the image figures. Okay, intervisibility. So for the intervisibility, actually we can compute what means by intervisibility. Can compute an attribute value for each cell according to the visibility of the cell from one or more viewer point. So based on layers of elevation, you can make a viewer location object. So from here you can see how far the visibility of your eyes actually can look far beyond. So we also have learned already the direction here. Uh, so an azimuth. So the azimuth goes similar what that have been learned from the previous slide, right? Azimuth, and also this horizontal field of view. Okay, from here you can move x, y, and also can move z, go down and go up. So from here we can make a screening. So we can get the surface of the earth level. So from there we can work how they want to create cutting filling area to do some project also. So it begins with the survey, then it get all the coordinates and then put into some of the data collection like coordinate, then it put into the GIS. So from GIS the map can create the DTM. So at last we can propose whatever task that you want. Like you can see the intervisibility analysis, they should have the layers, each layers, target. So from here we can look, for example, like this layer shows to you about the topography. We need the topography data, surface feature location, the height. So all of this might be, it gives some idea the data need to make some projects. And viewing position. So viewing position, and this one the data that has been collected from the viewing positions. So from there we can target whatever object that we want, and then from there we can get the intervisibility map showing area visible from one or more viewing position. Okay, good. Then we go to the DTM visualization. So for this DTM digital terrain model visualization, we have contouring, we have relief shadings, image combination with 2D data, and also the perspective display. So if you look contouring, so what means by contouring? So of course, you know already the contour line, widely used technique for displaying a relief. So they have contour. Sometimes it will be consistent. For example, like if the level is 5 meter, 5, 10, 15, 20, 25, and so on. And the construction of contour is closely related to DTM. Yeah, correct. Basic contouring may be further refined. So either we can use index contour and also contour label that can visualize very well to the map. As you can see from here, it shows to you, and normally the contour line, it will not overlap with each other. It will not. So there will be a different level. From here, you can see the difference is 10, around 10 meter, 110, 120, 130, and so on. So we also can develop from convert it into binary contours. So it will be look like this compared with this one. Okay, next, relief shading. So relief shading is also important technique to improve the visual qualities of the map itself. So there are several techniques model available to produce relief shading using DTM in GIS. The most commonly used like a theory of Lambert, Gaussian law. So the formula into it. So the programmer program the theory, the equation, so that can definitely perform the relief shading. So this is how that they use one of the equation. So you can develop like this, very clear. Looks like tremendous image. We also have a combination with 2D data, where 2D data we combine together the XY. So from there we can get some visualized image. Actually 2D, but when we combine it, perhaps it look like 3D. It's 3D. We also have isometric shading. So isometric shading, the image visualize the color and perspective view. This is the next one. So hopefully that you understand. Before this, the overview of the what we call as the DTM visualization. Okay, next we go to the perspective view. So perspective view is try to simulate the observation in the real world vision. So this have a parameter that need to be specified for the viewer relative position to the plane to be visualized. So distortion, where if it has a distortion, it will be to make the view more realistic. So there will be additional 2D information and also 3D surface in the perspective view that you will be a good view as you can see from here. So we can rotate it north to south, south to east to so some of the at least you have done it before in Google Map. You have put it on the north, south. You can see also at the back and bottom of the surface itself. So all of this they use in the perspective view parameters. So as you can see, they have a location. From there you can move it. Go at the right, at the left. So on the top and also at the back. Okay, so they also have a draping with satellite image. So this is one application also they use for DTM, draping with vectors and aerial photo. And they also input together with vector and also aerial photo that they get might be from aeroplane, and nowadays they use only drone. So they can combine together. So it will look like this. Very beautiful together combination vector, and also you can wrap with the object itself. So it put also the object into the map, so it looks very clear, realistic. Some of that maybe they also can make as an animation and virtual reality. It look like a very real. For example, like this Mount Everest. You can see, maybe you can zoom it. So if they have a good picture, application from the measurement, the instrument that they can capture all the image. Okay, so therefore, Alhamdulillah, so we finish already this lecture number 9. So the summary, we noticed that we can actually the land surface can be modeled as continuous three-dimensional space. So the DTM technique, we understand also the common geographic morphometric variables. Also, we understand already. We have learned already about the slope, aspect, curvature. So where is the slope? Where is the aspect, curvature from the image, from the figures? Also, we learn already the hydrological models to get the flow, the movement of the flow. And last but not least is using DTM, and we can visualize also in a numerous way. For better visual impression, like I mentioned just now. There's a lot of visual impression that can be good for us, so that we can make based on our project, what kind project that we want to solve, inshallah. So without further ado, so I think that's all for lecture number 9. So maybe you can repeat again to look, so then you can make some understanding in this lecture. So without further ado, so Assalamualaikum. So we continue with the next lecture. Thank you very much.